Quantum mechanics is the single most successful view we have of the physical world. It has passed every test for a century. Yet, physicists still haven't answered its most basic questions, not because of technical hurdles, but because the answers involve the very nature of reality. This is a top-down view of the double-slit experiment. When we fire individual electrons at these two slits, they don't act like small solid particles. They behave like waves, passing through both slits simultaneously to create an interference pattern of bright and dark bands on the screen. But something happens when we try to detect which slit the electron actually passed through. The moment we measure it, the wave-like interference disappears. The electron suddenly acts like a particle, landing as a single definite dot on the screen. This is the measurement problem. The standard equations of quantum mechanics use terms like measure and observe as if they are distinct physical actions, but they never define what a measurement actually is or why it should cause a physical wave to suddenly collapse. For most of the 20th century, physicists relied on the Copenhagen Interpretation, famously associated with Niels Bohr. This view argues that the wave function isn't a real physical thing, it's just a tool, a way to calculate the probability of where a particle might appear when we look for it. To maintain this logic, Werner Heisenberg and his colleagues drew a line between the quantum system being studied and the classical world of the observer. This dividing line, known as the Heisenberg cut, suggests that different laws of physics apply to the electron than to the scientist watching it. But scientists and their measuring tools are made of atoms, and atoms obey the laws of quantum mechanics. There is no physical evidence for a cut where the rules of the universe suddenly change just because an object is large enough for a human to hold. This leads to a different approach. Instead of assuming the wave function is a trick, what if we treat it as the complete, literal description of reality? What happens if we stop treating the observer as something outside the laws of physics? By declaring that the quantum world is essentially inaccessible when we aren't looking, the Copenhagen view discouraged researchers from asking what is actually happening. Taking the math literally offers a way to fill that 100-year-old silence. If we take the math literally, the wave function represents reality precisely. It never collapses into a particle. Instead, it continues to evolve according to the Schrodinger equation, regardless of whether a human is watching. In this framework, measurement is just a physical interaction. When a scientist observes an electron, they become entangled with it. Their own quantum state becomes linked to the state of the particle they are measuring. Because the electron is in a superposition of different locations, the observer enters a superposition too. This results in branching. There is one version of the universe where you saw the electron in position A, and an identical version in position B. This is the many worlds interpretation.
It isn't an extra assumption added to the theory. It is simply what the Schrodinger equation predicts if we refuse to edit the math to fit our everyday experience. Parallel worlds are the logical consequence of trusting the equations. If the wave function is real, then every possibility it contains must be real as well. When we apply this same literalism to the entire universe, we have to reconcile the quantum world with gravity. This requires finding a wave function for the whole of spacetime. This leads to the Wheeler-DeWitt equation. For decades, physicists have used this formula to describe the quantum state of the entire cosmos. When you solve this equation for the universe, the term representing change over time equals exactly 0. The math indicates that the underlying state of the cosmos is static. It does not evolve. If the universe's description is unchanging, time is not a core feature of the quantum bedrock. It suggests that the ticking clock we experience isn't part of the basic laws of nature. Instead, time is an emergent property. Our experience of time is tied to entropy, the progression from order to disorder. As this organized structure breaks apart and scatters, we perceive that sequence as a flow from past to future. In this view, time is a macroscopic perspective. It is the way humans experience the universe as it becomes increasingly disorderly. This quantum approach also changes how we view the Big Bang. Classical physics leads to a singularity, a point where the density is infinite and the math fails. But a purely quantum model avoids this breakdown. If we assume the universe has a finite number of possible quantum states, the math of the Schrodinger equation suggests the system must eventually return to its starting point. This creates a cyclic timeline. an expansion from a dense state that eventually curves back toward a contraction. Our universe is currently expanding and cooling toward a state of maximum disorder, but in a cyclical model, the cosmos eventually begins recontracting. This crunch mirrors the Big Bang, eventually resetting the cycle in a deterministic loop. By relying on quantum logic rather than classical singularities, the beginning of our universe is transformed from a unique magical event into one stage of an eternal process. This cycle raises a question about the contraction phase. If time is defined by the direction of increasing disorder, what happens when the universe begins to shrink back toward a dense, ordered state? Because we define the past as the direction where entropy was lower, the arrow of time is tied to the bounce itself. Entropy increases as the universe moves away from that low point in either direction. For observers, time always flows away from the bounce. This means that if we could see the other side of the cosmic crunch, time would appear to be moving in reverse. To any observers living there, their past would be toward the crunch, and we would be the ones living in their future. Concepts like many worlds and a bouncing universe can feel like flights of fancy, but they are the results of taking our most successful equations at face value. When we trust the math over our intuition, a much larger reality begins to emerge.